What is performance? Understand performance. Algorithm determine number of operation execute. Programming language compiler architecture determine number of machine instruction execute per operation. Processor and memory system determine how fast instructions are executed. Input-output system, including operating system, determine how fast input-output operations are executed. Response time and throughput. Response time, how long it takes to do a task. Throughput, total work done per unit time. Task, transaction or per hour. How are response time and throughput affected by replacing the processor with faster version, adding more processor. We'll focus on response time for now. Okay, relative performance, define performance 1 per divide by execution time. Y is at time faster than Y. Performance X divided by performance Y equal execution time divided by execution time X. For example, time taken to run a program. 10 seconds on A and 15 seconds on B. Execution time B divided by execution time A. 15 divided by 10, so equal 1.5 seconds. So this means A is 1.5 times faster than B. Here you can see if you want to find time taken of A, so B must divide by A. Okay. Another example. 60 seconds on A and 30 seconds on B. So execution time B divide execution time by A if you want to find the A. So the total is 0.5. So A is 0.5 times faster than B. If we want to find the B, education time A must divide by education time B. So the answer is B is 2 times faster than A. Measuring execution time. Elapsed time, total response time include all aspects. Processing, input, output, operating system overhead, idle time, determine system performance, CPU time, time spent processing a given job, discount input output time, or other job share. Comprise user CPU time and system CPU time. Different programs are affected differently by CPU and system performance. CPU clocking. Operation of digital hardware governed by a constant rate clock. So clock rate cycle, data transfer and computation, update state. To find the clock period means duration of clock cycle. Example, 250 per second equal to 0.25 nanosecond equal 250 times 10 minus 12 second. Clock frequency rate, cycle per second. For example, we have 4 gigahertz, that means 4 change to megahertz times with 1000 or equal 4.0 times with 10 times 9 hertz if we want to find in hertz. CPU time equal to CPU clock cycle time with clock cycle time equal to CPU clock cycle divided by clock rate. Performance improved by reducing number of clock cycle, increasing clock rate. Hardware designer must often trade off clock rate against cycle count. CPU time example, computer A, 2 GHz clock, 10 seconds CPU time. Designing computer B, aim for 6 seconds CPU time, can do faster clock but cost 1.2 clock cycle. Okay, clock rate B, minus with CPU time B equal 1.2 times clock cycle A divided by 6 seconds CPU time. Okay, instruction count and CPI. Clock rate equal to instruction count times cycle per instruction. CPU time, instruction count, time with cycle per instruction, time clock cycle time equal instruction count time cycle per instruction per clock rate. Instruction count for program determined by program, ISA and compiler. Every cycle per instruction determined by CPU hardware. If different instructions have different CPI. Every CPI affected by instruction mix. CPI example. Here you can do your by own self. Okay, calculate. Here this example. So A is faster by 1.2 by this much. Okay, this is how to find the clock cycle and wait average clock per second. Okay, you can check this and do by your own. Okay, performance depends on algorithm affected by IC, possibly CPI. Programming language affect IC CPI. Instruction set architecture affect IC, CPI, and TC. Reducing power. Suppose a new CPU has 85 second, 85 percentage of capacitive load of old CPU, 15% voltage and 15% frequency reduction. Okay, power new, power old. See how to calculate. The power wall, we cannot reduce voltage further. We cannot remove more heat. So how is we can improve performance? Multi-core microprocessor. More than one processor per chip. Require explicit parallel programming. Compare with instruction level parallel. Hardware execute multiple instructions at once, hidden from the programmer. Hard to do programming for performance, load balancing, and optimize communication and synchronization. Spec CPU benchmark program used to measure performance, supposedly typical of actual workload. Standard performance evaluation compression. Spec CPU 2006. Okay, normalized relative to reference machine, summarized as generic mean of performance ratio. Okay, cost of performance is improving due to the underlying technology development. Hierarchical layer of abstraction in both hardware and software. Instruction set architecture, the hardware or software interface. Execution time, the best performance measure. Power is a limiting factor. Use parallelism to improve performance. Evaluation method, Amdahl law. Amdahl law implies that overall performance improvement is limited by the range of impact when the optimization is applied. Consider the following equation. Improvement rate, original execution time, per divided by new execution time, new execution time equal with time unaffected plus time affected divided by improvement factor. time equal instruction count, time with CPI, time CCT. CPI equal execution time, time clock rate, divided by instruction, CPU as time, B, divided by CPU time A. Amdahl law. For example, if a program currently take 100 seconds to execute and load and store account for 20 seconds of the execution time, how long will the program take if load and store are made 30 seconds faster? For this, you can use Amdahl law or you can reason it out step by step. Doing it step by step give one before the improvement load take 20 seconds. If load and store are made 30% faster, then they will take 20 divided by 1.3 equal 15.385 seconds, which correspond to 4.615 seconds less. 3. Thus, the final program will take 100 minus 4.615 seconds equal with 95.38. Amdahl law, named after computer architect Jean Amdahl, is used to find maximum expected improvement to an overall system when only part of the system is improved. Amdahl law can be interpreted more technically, but in its simplest term, it means that it is the algorithm that decides the speed up, not the number processor. Amdahl law is demonstration of the law of diminished return, why one could speed up part of a computer 100-fold or more. If the improvement only affect 12% of the overall task, the best the speed up could possibly be is 1 divided by 1 minus 0.12 equal with 1.136 times faster. More technically, the law is concerned with the speed up achievable from an improvement to a computation that affect a proportion P of that computational where the improvement has a speed up of S. For example, if an improvement can speed up 30% of the computational, P will be 0.3. If the improvement make the portion affect twice as fast, S will be 2. Amdahl law state that overall speed up of applying the improvement will be 1 divided 1 minus P plus P per S. To see how this formula will derive, assume the running time or the computation 1. For some unit of time, the running time on the new computation will be length of time. The unimproved fraction take, which is 1 minus P, plus the length of time the improved fraction take. The length of time for the improved part of the computation is the length of the improved part former running time divided by speed up, making the length of time of the improved part P divided by S. Okay, you can do this work and do the calculation. Here is an example. Okay, you can find. And this how to calculate. Okay, that's all. Thank you.